All right, so let's get started. Welcome to the Global Math Department. My name is Lee Natero, and I will be your host tonight. Tonight, we're going to be hearing from Dave Ebert about global mathematics, an elective mathematics class for all students. Would everyone please introduce themselves in the chat window, telling us what you teach, where you teach, and what your Twitter handle is, if you have one.
All right, Lee, and while people do that, I'm going to jump in and get started. Lee, can you hear me okay? Are we good?
You're good. I actually did want to introduce you.
Oh, yeah. Okay, go ahead.
Yeah.
I thought I'd start introducing myself while people were doing the same.
Nope, I will introduce you. So Dave Ebert teaches kids how to do, appreciate, understand, and love mathematics at Oregon High School in southern Wisconsin. He's been teaching students in grades 6 through 12 for over 20 years. And he recently served on the board of directors of the National Council of Teachers of Mathematics. And he also is a past president of the Wisconsin Mathematics Council and has held multiple leadership roles in both organizations. Dave has presented and led workshops for teachers on a variety of topics at the local, state, and national level, and he has won several different awards for teaching. He was recently honored as the Wisconsin Mathematics Council Distinguished Mathematics Educator. So welcome, Dave.
All right, Lee, thank you very much, and thank you to the Global Math Department for inviting me to present. I'm honored that everyone would give up some time to join me tonight. And, you know, there's so many things going on in our world right now that are bigger than all of us. And to me, it's just a reminder that we all need to remember that we teach more than math, that we are more than math teachers, that we're teaching our kids, and we're teaching, what we're doing is more important than any of us. So I'm really excited to get going here. So what I want to share with you tonight, I teach a class at my high school. So I'm a teacher in Wisconsin, and I teach pre-calculus and statistics and a course called Global Mathematics. And so I'm going to share with you some of what I do in that class. And I also, before we start, I'm going to welcome you. So on this cover slide here, I've got my email address. Please feel free to reach out to me. I'm willing to share this presentation, any course materials I have, course outline. And when I proposed this course to my school board, I had to submit a new course proposal. I'd be willing to share that as well and just help you with any efforts you have to either teach a course like this or to involve elements of this in your courses. So Lee mentioned that I actually just finished my term on the NCTM Board of Directors. So just to start, I have a gift for all of you. So if you would like to jot this down, and then if you either join NCTM as a premium member or renew your membership and type in this code at the checkout, it will give you a $20 discount. So this is not just for those in this session, this is for your colleagues, your friends. So feel free to share this. Love to get more of you involved with NCTM. Now, before we start, I'm just going to share a quote that I heard from Sunil Singh about a month and a half ago with the Global Math Department presentation that he gave. He said, to involve people at the deepest level, you need stories. And he was presenting on utilizing math history to embrace equity, failure, and authentic problem solving. And I'm going to touch on a lot of those themes tonight. So I really like that quote that we need to involve stories, that our math that we teach shouldn't just be the dry mathematics out of our textbook, that we need to involve the stories of the mathematics and the discovery of the mathematics and share that with our students. So our outline tonight. So we're going to start talking about why even have math electives. And if you're going to have math electives, why this one? Why global mathematics? And then I want to share with you a course outline, course materials, and you are welcome to ask questions throughout. We're going to be doing some mathematics throughout. So if you don't have it in front of you, everyone's going to need paper and pencil. And I'm also going to ask you to answer some prompts in the chat. So make sure you're ready to go with that. So take a second to grab something to write on, something to write with, because what fun is a math presentation if we're not going to actually do some mathematics along with it. Okay, so first thing I want everyone to think about, I found this quote, and I want to know if you agree or disagree with this. So this quote, mathematics is often thought of as a culture-free subject. Take about 20 seconds to just think about that quote. And then I'd love to hear some of your thoughts in the chat, please. So think about that quote. Let's put some thoughts in the chat, and then we'll kind of see what comes out of this. And it's awesome just seeing all the people jumping in on the chat right now. Also interesting, you know, we've got different levels of agreement and disagreement. And it is interesting too with this audience. We've got people from all over the world with this audience right here. I've asked this question of teachers here in the United States, and I'm sure the responses that I'm going to get here are going to be much different than the responses that we're going to get tonight. Okay, and feel free, if you're typing a response, feel free to keep typing that. But like I said, see a lot of different, this would be a wonderful place if we were together. We would turn and talk and discuss and share. But, you know, seeing a lot of different ideas come up in the chat. And to be honest with you, the school mathematics that we teach is very European. It's very Eurocentric. Okay, and there's a lot of my students don't have a connection to the math that they learn or the math that they have learned for the last 10 years in their school career. And I'm going to share with you something that was shared with me by Gloria Latson Billings, who is a professor at the University of Wisconsin. She said there are 3 things that challenge students of color. 1, the belief in math as cultural neutral, saying that when math is thought of as culture neutral, that this challenges students of color. Second thing is limited access to good teachers, that our good teachers are often not spread out over the districts that need them the most. And the third is that limited access to good curriculum. And we're really going to address that first item tonight, the belief in math as culture neutral. And we can think of a lot of different examples of this, and we need to figure out, though, how do we build all of our students' math identities when all of our students can't identify with the math we teach? So one example to share with you is the Pythagorean Theorem. So the Pythagoreans lived in southern Italy. Pythagoras lived from about 570 to 495 BC. And I just want you to focus on that date right now, because I want to share with you some other instances of the Pythagorean Theorem. This right here is, this stone was found in southern Iraq. It's called Plimpton 322, based more on the person who owned it. It's named after the person who owned this when it was found. And this was carved in about 1800 BC. Many, many years before Pythagoras even lived. And it was carved on a clay tablet using a cuneiform, which is a metal carving instrument. And what these items are, if you look at the middle and the column to the right of the middle, these are numbers that give Pythagorean triples. So there's this definite evidence that the Babylonians in southern Iraq knew of Pythagorean triples well before Pythagoras even lived. And there's also evidence that people in Egypt and China knew of the Pythagorean theorem as well. But yet we teach our students of this Pythagorean theorem. We may stretch ourselves and talk about Pythagoras, but we rarely mention in our classes that this theorem was known by people all around the world before Pythagoras even lived. And something else really interesting about this tablet, the numbers on the far left-hand side are actually decimal numbers, and they are ratios between the sides of the triangles. So this is more than a table of Pythagorean triples. It's a trigonometry table. So what you see on the side, the ratio between sides of those triangles, is used to do trigonometric calculations. This is pretty amazing that this was around in 1800 BC, which might lead you to think, who would ever use this? Why was this around? And historians believe that this was used by a teacher, and teachers would use tablets such as these. In fact, this tablet here is about the size of a small notebook. So this tablet was used by teachers to create mathematical problems for their students. So I've got another question I'd like you to discuss in the chat as well. So next thing I want you to think about, what do you think? And this is one, it's okay to not know the right answer to this. The vast majority of us probably do not know this. I would hazard that none of our students know this, but what do you think is the earliest evidence of mathematical thinking? When do you think this occurred? Now we saw some, I'm just going to flip back here. We saw some pretty old evidence here, 1800 BC. But what do you think is the earliest evidence? It's got to be before then of mathematical thinking. When do you think this occurred, and where do you think this occurred? And I'm going to be quiet for a while to let you think about that, and love to see some of your guesses in the chat. And again, I'm seeing a lot of different ideas coming here. Want to finish what you're typing? And I did see the answer I'm going to share with you go by in the chat. So let's just go to the next slide here. So this is what's called the Ishango bone. It was found in Uganda, and it's been dated to 20,000 BC. And Ishango is the region where it was found. And this bone, this is like a forearm bone of let's see here, of some primate. Now, there's actually earlier instances of bones being used to tally, to count. There's something called the Lobombo bone from 42,000 BC that has tally marks on it. And the mathematical historians will argue with you whether just counting counts as true mathematics or not. So you might say, what does the Ishango bone offer that goes beyond just counting? Well, there's marks on both sides of the bone. On one side of the bone, here's the number of tally marks. So on one side of the bone, the marks go, there's 3 marks and then 6 marks. Then a little farther along, there's 4 marks and then 8 marks. And a little farther along, there's 5 marks and then 10 marks. So 20,000 years ago, someone was thinking about this idea of divisibility, about this idea of doubling. Now, that's pretty exciting, but if you turn the bone over, you'll find something even more fascinating. On the other side of the bone, there's a group of 19 tallies. Then there's a group of 17 tallies. Then there's a group of 13 tallies. And then there's a group of 11 tallies. And the fascinating thing, we all recognize these now. These are prime numbers. These are numbers that are not divisible by any number other than 1 in itself. So whoever was making these marks on this bone was thinking a lot about divisibility. And so math historians will say this is the first evidence of higher level thinking in mathematics. Now, here's the question then. Why don't our students know this? Why don't we know about this? We all teach about divisibility. We all teach about prime numbers. Why is this not in our curriculum? Why is this not put up there? And here's something else really fascinating about this. So here is Uganda. Here's the region in the world where this bone was found. And this is really the cradle of all civilization. But in your history classes, when you study Western civilization, it usually starts with Egypt and Greece and Italy. But really, intelligent thought started here in Central Africa. Then it flowed up the Nile to Egypt, and from there it spread throughout the Mediterranean. Now let's think about this. How empowering is this to our African American students to know that all intelligent thought started in Central Africa? And why are we not sharing this with our students? This to me is this is something that we must be sharing with them, because this is something that is just potentially empowering to all of our students. Okay, so let's jump into the presentation. So big question is, why should we offer a course in global mathematics? Or if you're not offering a course, why are we not offering more of these global ideas in the courses we teach? So one big reason that we should have a course like this is equity. We currently teach the mathematics of Europeans, and we need to spread that out. We need to broaden our idea of what mathematics is. And going back to a question I asked before, how do we build all of our students' math identities if we teach nothing but European mathematics? Okay, a second reason why we should teach a course like global mathematics is we need to reevaluate our curriculum through a social justice lens rather than a college and career lens. You know, the college and career lens is great for a number of our students, but it doesn't hit every one of our students' needs. Third reason why we should teach a course like global mathematics is that not every student needs the same learning pathway to achieve the same goals. Plus, not all our students have the same goals. There's a lot of discussion nationally about Algebra 2 right now, and is Algebra 2 really necessary for all students? Is this a need that all students have? And I'd argue that for our college-bound students, yes, perhaps they should get in an Algebra 2 kind of class. But for those not, maybe something like global mathematics would fill their needs in a different way. And you think about other subject areas. In my school's history department, in my school's English department, in my school's science department, students can take electives. Their first couple years, they all take the same courses, and then their junior and senior years, they can elect which courses are interesting to them and which courses fit their future needs. Math, we have this progression of algebra, geometry, algebra 2, pre-calculus, calculus, and offering some electives like global mathematics gives students something that fits their needs much better. Okay, fourth reason we should offer something like global mathematics is because we all need to expand our thinking of what mathematics really is. And back in 1989, NCTM released their standards and said, this is what math is. It's problem solving. It's reasoning. It's making connections. It's communicating. And you think about this this is like 30 plus years ago now. And our classes are still really focused on algebra, geometry, algebra 2. And we need to think of math a little bit differently. All right, fifth and final reason we should offer courses like global mathematics. NCTM just released a book within the past couple of years called Catalyzing Change. And when I read this book, I was smiling, I was kind of jumping off my seat, and it really verified the work I did in creating this course. Because in Catalyzing Change, it says that our students need to understand and critique the world and experience the wonder, joy, and beauty of mathematics. And this is often missing in our curriculum, and this is something that we can all bring to our classes. So I'm just going to bring some quotes from that book. And you'll notice that Lee put a website in the chat. If you're interested in getting that book or looking into it more, check out that website. But some quotes from the book, and this is early on in the book, says it is critical that all students study other mathematics beyond these essential topics. And I think the keyword there is beyond. We need to look beyond the essential topics that we currently teach, and recommendation that students have 4 years of continuous engagement in mathematics at high school. Here's another quote from early in the book. The pathway of courses that students follow will vary and should be based on students' interests and aspirations. So this sounds a lot like moving away from that Algebra 1, Geometry, Algebra 2 sequence. Another quote from the book, high school math empowers students to expand professional opportunity. Yes, I would argue we do a good job at that. Understand and critique the world. I would argue that we need to do a better job at that. And experience wonder, joy, and beauty. I would argue that we don't do a good job with this, and we need to do a better job with this. Farther along in the book, another quote, high school mathematics should strive to highlight the contributions of a variety of cultures. Imagine that, not just Western or not just Eurocentric contributions. Farther in the book, I won't read this whole one, but something about halfway down says, high school mathematics programs should give students an appreciation of what mathematics is and how it can be useful in their lives. All right, one last quote from this book, and then we'll move on. So last quote towards the end of the book, the final couple years of high school mathematics could offer students a variety of courses, including history of mathematics, which is what we're going to dig into here tonight. Okay, so I want to share just some of my journey of, when I created this course. I really wanted to expand offerings for my advanced students. And the first time I offered this course, I had a kid in class who aced the ACT, so pretty advanced kids. I also wanted to offer options for students in need of credits. And again, that first time I offered this course, I had 3 students in my course who needed to pass the course to graduate high school. So I wanted to give a wide range of students a different reason for taking this course. And the main reason, though, is that third one. I want our students to study mathematics because it's interesting and beautiful, not just to prepare for the next course. And in fact, day 1 of global mathematics, I say to my students, we're not preparing for the next course. We're not preparing for a test. We're learning what we're learning in this course because it's interesting. And I think that gets the hook in right away. So when I first started thinking about designing this course, I looked at some other things going on in Wisconsin. So Wisconsin, where I teach, has a global education certification. And my own high school has a global education achievement certificate. So students earn 8 credits in a bunch of global related courses, like their foreign language courses. We have a Go Global course where students travel around the world. We have international marketing, global art, global cuisines, and of course, global mathematics. So if students take 8 total credits in these courses, they earn a certificate along with their diploma when they graduate. All right, so starting to pull some materials together for this course. Here's some resources that I dug into. And this resource here, this was the number 1 resource I used. And this was actually the textbook I used when I took history of mathematics in college. There's some other good resources here too. That second resource, Rethinking Mathematics. So Gutstein and Peterson talk about the 3C framework for math knowledge. The classical framework, which is school math, the community framework, which is what is used outside of school, and the critical framework, which is looking at social injustices. All right, some other resources I used. This book here, it's a great one, Classic Math. There's also another book there, Journey Through Genius. So some other great books to look through. Here's another set of resources, Agnese to Zeno, over 100 vignettes from the history of math. The Story of Math TV series from the BBC. Oh, wonderful. If you haven't seen it, get on Netflix and watch that as soon as you can. Okay, and there's plenty of other resources out there as well. So I finally pulled everything together and I was ready to go. And here's the outline for the course that I teach. So there's 6 total units, and these 6 units follow a historical timeline. So the first unit of the year is on number systems, and we'll dig into each of these units here in just a bit. Second unit on Greek mathematics, third on Eastern mathematics, then back to European mathematics, and then we move away from history and get into global problem solving. And the student's final exam is a final presentation, which I'll talk about at the end of this presentation tonight. So now that we've kind of seen some background, some resources, let's get into these units one at a time. So the first unit in the course I teach is number systems. And here's some of the topics that we touch on. So primitive counting, early number systems. So we talk about how Egyptians and the Greeks and the Babylonians, Romans, Chinese, Japanese, Mayan, we talk about how all these different cultures use numbers and how their numbers are different from the numbers we use today. Talk about early operations. And then presentation. So at the end of every unit, I have the students present on something in more depth. So when we learn something in class and they say, that's really interesting, I tell them, remember that, because at the end, you're going to present on this topic. And then they present to me some things that they dig in and learn. And I learn so much from these presentations. It's a wonderful way to share information back and forth. So here's what I want to do. I want to get into some of the math from this unit. So I told you at the beginning to make sure you had paper and pencil handy. This is your chance. So grab that paper, grab that pencil. We're going to be doing some mathematics together. And this is from this first unit. So what I want you to write down is this multiplication problem. And what we're going to do is what's called Russian peasant multiplication. Now, even though that's the name of what we're doing, this is used all over the world. This was used in Egypt. This was used by the Babylonians. And the reason it works out well is because it is really easy to double and have numbers using an abacus. But being able to multiply something like this is really hard to do with unless you have a multiplication table. So for people who don't know how to multiply or don't have a multiplication table, this method will work for them. So you've written down the problem. Here's what I want you to do. Underneath each of those numbers, in the first column, I want you to cut that number in half. And in the second column, I want you to double that number. And we're just going to keep following that same process. So the first column, you're going to cut that number in half every time. The second column, you're going to double that number. And you probably already see an issue with this, because if you cut that first number in half, what happens? Do we keep a decimal? No, we actually just truncate the number. So if you cut a number in half, you can just forget that 1/2 or 0.5. So keep going down. Cut the first column in half, double the second column, and I will do the same. So if you are struggling to halve and double, the halves are probably okay. The doubling gets a little challenging. So if we keep doing that until we get to a 1 at the bottom of the first column, and then we can stop. Okay, so I said in the beginning, this works well if you can have and double numbers real easily, because here's our next step. What we're going to do is we're going to cross off all the rows that have an even number on the left. So every row you have that has an even number on the left, cross those off. All right, now here's the amazing thing. If you add the numbers that remain on the far right, that will always give you that answer. And oftentimes my students, they're amazed by this. And it's really interesting. When I share this with my students who struggle say, why weren't we ever taught this method? They love this method. They say, why wasn't I taught this when I was struggling with multiplication in elementary school? And my students who thrive say, why does this work? And this is where I say, this is where you need to dig into this more, and you're going to present this to your peers at the end of the unit. And if you doubt this, if you think, okay, this only works for this example, I encourage you, jot down some more examples you make up on your own and try it out. And just to answer a few questions, half of 9, remember, we just truncate, we get rid of the 0.5. And someone else asked earlier if this was a semester elective or a full year. This is a 1 semester elective course. Okay, and I could see it expanding to a full year. I could see this being used at the middle school level, but for me, I use it as a 1 semester elective course at the high school level. Okay, so that's just an example of some of the mathematics that we do. And last question here, the numbers on the far right-hand side, so the numbers that aren't crossed off, we add those together, we will get our answer. Okay, let's get into our second unit. So the second unit is on Greek mathematics. And when I say Greek mathematics, I really mean mathematics around the Mediterranean. So talking about mathematics in Italy, in Egypt. In fact, Alexandria was the center of the intellectual world. The greatest school in all of history was at Alexandria, which is interesting. It was in Egypt. It was in Africa. So in fact, when you buy an Alexa and you say, Alexa, what time is it? It's named Alexa after the school in Alexandria. So here are some of the topics that we study in this next unit. So we start to get into algebra and geometry. Now, what the Pythagoreans called algebra is more like what we call number theory. Okay, so their algebra looked a lot different from our algebra, but they really distinguished between the algebra and the geometry. And interesting, now I have names of mathematicians. One name I should have put up there, I apologize for not putting this, is Hypatia. Her name should be there as well. But the interesting thing is this is the first time in history we know the names of mathematicians. We also get into proofs, practical applications. So the Greeks studied math for practical purposes, for defense, for music, for physics. In fact, the Pythagoreans studied the mathematics of sound, and this is the first. We're talking about the history of math, but if you talk history of science, this is where that course would begin. And then again, at the end of the course, the students, or at the end of the unit, the students give presentations. So again, I want to share some mathematics. Hopefully you haven't put that paper aside. Maybe some of you are trying to multiply some different numbers at this point, but I'm getting into the next math problem we're going to dig into. So pick that pencil back up, grab that paper. And this goes all the way back to a mathematician named Heron. And this is Heron's method to approximate a square root. And Heron came up with this in about the year 50 AD, so about 2,000 years ago. And we're going to find the square root of 10 using this method. Now, interesting backstory here is my daughter was in middle school when I was developing the materials for this course. And one time I was sitting at the kitchen table developing the materials that demonstrated this method. And she said to me, "What are you doing?" And I said, "Well, you know, when you press your square root key on your calculator, how do you think that it knows the square roots of these numbers? Like, it doesn't just have a table in your calculator. It goes through some procedure to calculate it." And I said, "I'm going to share with you the procedure that your calculator may use." And it was developed 2,000 years ago by a guy named Heron. And here's what he did. So the first thing you do to find the square root is first find the factors of 10. And not all the factors, just 2 factors of 10. And when I offer this to my students, the vast majority of them say 2 and 5. This does work if you say 1 and 10, but it works better if you pick factors that are closer together on the number line. So we're going to go with 2 and 5. But if you want to try 1 and 10 and work along with us, that's perfectly fine too. So once you find those factors, we take the average of them. We add those 2 numbers and divide by 2. And if you don't want to do that calculation on your own, I've got that answer up there. It's 3.5. So now here's what we want to do. Every time we get an answer, we want to find the average of that new number and the original number 10 divided by that new number. Okay? So we're going to take 3.5, our answer, plus 10 divided by 3.5, and find the average of those 2 numbers. And if you do that, you get about 3.1785. Let's do that one more time. So here's what the next step is going to look like. It's going to be this answer plus 10 divided by that answer, and then divided by 2. So it's the average of this answer and 10 divided by this answer. And if we do that, we get a number around 3.1623. Now, if you have a calculator handy and you type in the square root of 10, you will get an answer that's remarkably close to this. And the more steps you take, the more accurate this square root will be. But the amazing thing is we only took 3 steps. We did 3 calculations, and we got an answer that is surprisingly close to the square root of 10. When I show students this, they're amazed. They are picking numbers on their own. They're saying, let's see if it works for 20. Let's see if it works for 50. Let's see if it works for 2. And they're just trying these different numbers and coming up with these square roots on their own. And they feel so empowered to know this is how their calculator works. This is how their calculator comes up with these square roots. Now, I don't really know if their calculator has a more efficient method or not, but I think this is a pretty efficient method on its own. And it was developed by some person living 2,000 years ago, which I think is pretty amazing. So next time we teach square roots to our students, why don't we share this method with them and share some of the history and share that story of Heron. Heron's an interesting guy just on his own. So if you look up Heron, you'll find all kinds of interesting things about him. And again, get your students interested in the mathematics you're teaching. Okay, so first unit was on different number systems. Second unit was Greek mathematics. The third unit in this course is on Eastern mathematics. And this is the math of China, India, and Persia. And the interesting thing about studying this region of the world is that we know that the people in these countries traded with each other. And the reason we know they traded is because of math. Because every time there's some new discovery in China, you'll find evidence of that discovery in India about 25 to 50 years later. Anytime there's something new in India, you'll find that evidence of that discovery in Persia 25 to 50 years later. And anytime there's something in Persia, you'll find it in India. So there's this trade route between the 3 nations, and we know that they're trading and talking to each other because of math. We also know at this time that Europe is not trading with these people because this is the time, this was the Dark Ages in Europe. So there was no new mathematical growth for over 1,000 years in Europe. Nothing new going on. Basically, the European nations were fighting each other. They weren't devoting time to new math or scientific discoveries, but Asia thrived at this time. So mathematics just exploded in Asia at this time. And some things that they developed were the decimal system. Negative numbers, which were initially developed as profits and debts. They developed the Pythagorean Theorem, put it in quotes there because obviously not named after Pythagoras. Pascal's triangle, we have evidence of that hundreds of years before Pascal lived in India and in China. They used algebra, they used trigonometry. They were the first to develop an idea of zero and an approximation of pi. Here's something else interesting too. Recreational math was developed at this time in this part of the world. So this is the first time math was used for games and puzzles, and it's awesome in a class to, you know, when it's that Friday before homecoming and students aren't very focused, you pull out some recreational math games and puzzles from this part of the world, and students are hooked. And again, I end the unit with presentations so that I can learn from my students. Okay, so again, let's do some mathematics from this time. So grab that paper again, grab that pencil. Some of us are probably still working on those square roots. That's perfectly fine, but let's jump into a story. So this story is regarding the Lo-Shu magic square. And we have evidence in writing of this from about 1150 BC. And the story goes that Emperor Yu saw this diagram on the shell of a tortoise in 2200 BC. Now, this diagram, you might look at this and say, okay, it looks interesting and all, but if you count the dots in each of the spots, so in the upper left corner, there's 4, below that, there's 3, below that, there's 8. If you count those dots, it makes what's called a magic square. Now, what makes a magic square magic is that if you add any row, add the numbers in any column, add any diagonal, you get the same value. So students see this, they're intrigued, they want to know more. And so I say, okay, so let's make our own magic squares. And this method that we're going to use today can be used for any odd number by odd number magic square. So we're going to use this method on a 5 by 5 magic square, but if you wanted to use it on a 3 by 3 or a 9 by 9, it would still work. So I want you to draw a grid, a 5 by 5 grid, and place the number 1 in the top middle spot. And to be honest, that number 1 can actually be placed in a number of different places, and this will still work. The method we're going to be used can be modified a number of different ways, and it'll still work. But here's how you can make a magic square. So what we're going to do is we're going to write down the numbers following from 1, but we have to do it along a diagonal. So we're going to follow a diagonal that goes up and to the right. And if you go up and to the right, you might say, wait, we're going off the square. So that's perfectly fine. We can think of the square as wrapping around, and that would take the number 2 down to the bottom row. Let's continue. So let's go up and to the right to write a 3. If you go up and to the right, you might say, wait, we're going off the edge. Well, think of the square as wrapping around left and right as well. So if you go up and to the right, you can do that and you'll get a 4. And if you continue this on and on and on, you'll make a magic square. And you might notice right away that, if you do this a couple more times, you'll run into that 1 and then we're out of luck. Well, what we do anytime we run into a number that's already there is we write a number down below and then continue the diagonals from there. And I would invite you to continue those diagonals. It gets a little tricky when you hit the corners. Like, okay, if this is wrapping left and right, wrapping up and down, what's going on? So I'm just going to cut to the chase and share with you what that method will look like when you're done. And we have just produced a 5 by 5 magic square. If you add any row, if you add any column, if you add any diagonal, each one of those sums will be the same. Now, the students are hooked at this point. And I had 2 years ago, I had a couple girls present at the end of this unit on a different method to make these magic squares. And this different method worked perfectly well, and it amazed me. I couldn't believe it worked, and it was great. And, again, I was learning from my students, which really empowered those 2 young ladies. Now, magic squares can be found all over the place. You'll see these in Chinese mathematics. You'll see these in Indian mathematics. In fact, Benjamin Franklin here in the United States would make these magic squares when he went out socially. So he would go to a party and someone would say, oh, Ben, can you make me a magic square? And he would follow a similar pattern to this. And he didn't share what the pattern was. He would make these magic squares and astound the guests. And if you want more information, just Google Franklin Magic Squares. There's actually a book written on it, and I highly recommend the book. But, I could teach an entire, I think, a semester class on magic squares. There's so much history behind them. All right, so we've talked about 3 units so far: number systems, Greek mathematics, Eastern mathematics, and that brings us back to Europe. And history finally catches up with Europe. And in the year 1202, a guy by the name of Fibonacci, he was a wealthy European, and his dad hired a tutor for him. And his tutor was a Middle Eastern tutor. And his Middle Eastern tutor taught him some of the math that was being developed in Persia, in India. And Fibonacci was astounded. And he wrote a book called the Liber Abaci. And that book spread mathematical knowledge through Europe. So again, we've got all these names, and a lot of these names are well known by us. Some of them are well known by our students. But some of the big breakthroughs here were the printing press was invented, which allowed knowledge to be spread more easily. Metric system was developed. Astronomy was big, so science was big. And in fact, the development of logarithms allowed mathematicians to look at very large quantities and very small quantities. Up till then, science kind of hit a roadblock. They said, we know the moon is very far away, but there's no way we can calculate how far. But when logarithms were developed at about this time by Napier, it allowed scientists and mathematicians to really, dig into a lot more math. Probability was invented at this time. And again, presentations, I have the students present at the end of every unit. Okay, so let's do a little bit more math. So last time I'm going to have you do some mathematics. So I want you to pick up that pencil one last time. And famous mathematical problem. This is called the Bridges of Königsberg problem. And it was from 1736. And Königsberg was a city, it was a former German city. Now it's in Russia. It's now Kaliningrad, Russia. And the citizens of Königsberg would attempt to start at any place here and walk so that they would walk over every bridge exactly once without crossing over any bridge more than once. Okay, so they would attempt to start on one of the islands or one side, and there were these 7 bridges across these rivers, and this was like a game played by the citizens of Königsberg, and none of them could figure out how to do it, but they also couldn't figure out if it was impossible or not. So they contacted the greatest mathematician of the time, who was Leonhard Euler, and Leonhard Euler actually invented graph theory to solve this problem. So what he did is he took that series of bridges and he rewrote it as what's called a network. So that diagram on the right is the network. And then he said, okay, instead of walking, let's try to trace this with a pencil. So he drew this and tried to trace it, and he saw that there's no solution for this. And the reason there's no solution is because if you look at some of the points, there are an odd number of the lines that come out of those points. And the only way this can work is if there are either no odd numbers of lines or only 2 odd numbers of lines. And again, this starts fascinating our students, and they say, what other diagrams work? What other diagrams don't work? And they start developing their own. They start looking at ones. I tell them, try to challenge your friends. Make one that your friend can't trace. Make one that you can trace, but your friend can't trace. Now, one interesting thing, if you look at the lower right-hand diagram, this is not something from Euler, from Königsberg. This is actually what's called a Ishango network, and it's from the Congo. So children in the Congo make these kind of diagrams with their fingers in sand, and they try to make the biggest, most intricate ones. And if you look at this, there's 2 points on that diagram that have an odd number of intersections. So yes, this can be created. And the interesting thing with this too is, for my class, one of the biggest weaknesses of my course is that there's not enough on African mathematics, and there's not enough on on female mathematics. And 2 big reasons for that. African mathematics is lacking because in Africa, they really use an oral history, so there's not much writing on their mathematical discoveries. Female mathematics is lacking because for centuries, females were shut out of university level mathematics. So unfortunately, that makes it hard to bring in African and female mathematics. So I'm always on the lookout for more. And this diagram is just a wonderful example that I can bring into my course. Okay. So let's wrap things up. So those are the 4 mathematical units. Then we shift gears a little bit, and I'm just going to read a quote for you from John Staley. It is time for us to humanize the teaching and learning of mathematics so that students see value in the mathematics they are learning and how it extends beyond the goal of being college and career ready. So at this point, I shift into a social justice focus of mathematics. And the 5th unit in my course, we solve some global projects. And I took this matrix from something called EdSteps. And the 4 steps to solving a global project is to identify an issue, weigh relevant evidence, analyze, integrate, and synthesize evidence, and develop an argument. And these 4 steps sound very mathematical to me. Even though Ed Steps developed these for solving global problems, they're very mathematical. And I tell my students the math of today is used to solve the problems of today. And we need to prepare you guys to solve all the problems that we have created. And so some of the sample projects, so I basically find articles from my newspaper. And one article I found in the past year was talking about how a group was they basically created this nonprofit to supply solar panels to people in the Congo. Another newspaper article from a couple years ago, there's a Native American reservation near where I live, where when the students or when the residents there turn 18 years old, they get money from the casinos on that reservation. And we have a little debate, and people look at some of the mathematics between should they get all that money at once? Should that be invested for them? What would be a better way to get them that money? And then just a simple question, should I buy an electric car? This is something that we can study as well. And depending on the time we have left, we do at least one sample project together. I've had years where I've done all 3, not sure why some years we kind of go through things quicker than others, but then once we do a project together, or at least one project together, then their final project is that they need to select a topic of their own, select some world problem, and solve it using mathematical thinking. And this is an example of some of the projects that they have come up with. And if you read through this list, some of these are very timely right now. You can tell some of these were more timely in the past couple of years and were on their minds. I know already next year when I teach this course again, we're going to look at topics like patterns of disease, COVID-19, defunding the police. We can look at car financing, school funding, so many different social issues. And this really empowers our students to do projects on things that they are interested in. And I tell them their job is to go off and solve these problems, that we are counting on this generation of students to solve all of these problems. So I want to save a little bit of time at the end for some questions. Actually, a number of questions have scrolled through already, but I want to share one last quote. And this is the last message I want to send you off with. Not sharing diversity in our classes not only hurts our children of color, but also our students who don't ever learn the whole picture and the true story. So whether this is a course you can offer in your school or whether you can take some of these ideas and integrate them in what you're teaching, I firmly believe that it's very, very important that we share global mathematics with our students as much as we possibly can. All right. I am very, very willing to stick around as long as you guys have questions, but you are all free to send me an email. You're all free to that's my school website there. I have my class materials on that website. So if you go to that site, you can find the materials I use when I teach the class. My Twitter handle is there. So feel free to contact me. You know, I'm very, very excited when I teach this course. I'm very, very excited to share. And I would love it if this course or units from this course were taught all over the country, all over the world. I would love that. Okay. And I see one question right away, so sorry to interrupt you, but for the final project, it's their choice. They can choose to work individually or with a group. I tell them once the groups hit about 3, though, groups beyond that tend to not work very efficiently together. So I say groups of 1 to 3.
Yeah, I was just saying, I think you answered most of the questions throughout, but there was some good discussion with people sharing ideas throughout the presentation. There was one question about when do you hit up any math history related to Latin America? You know, Incas, Mayans, Aztecs. Is that anywhere in one of your units?
Yeah, I do some of that in the first unit on number systems. but I'll be honest. It's that's another weakness of the course, that it's I don't have an entire unit on that. We talk especially about the Mayan number system, and just how I think it's a fascinating base 20 system, and based on the 20 our fingers and toes that we have, and students really get into that. Why do we use a base 10 system? And even talking about the different bases, there's a culture right now in I believe it's a Pacific Islander culture that uses a base 27 system, which I never knew about, but a student presented on that a couple years ago, and yeah, and I digress. So with Latin America, really the emphasis is on the Mayans base 20 system. Beyond that, I'd love to hear more. If people have ideas they could share with me. Yes, I see the Kipus someone wrote down, and I share that too on the very first day when I talk about some of the ancient mathematics around the world, and that's one example of that. All right.
Yeah. Well, thank you very much, Dave. The presentation was definitely really informative. So I appreciate you sharing your knowledge and your resources with us.
Yeah, Lee, and thank you once again, and thank you to the Global Math Department for having me tonight. And I'm going to put out a plug for the Global Math Department, because if you take a look at all the presentations you guys have archived, it's very, very impressive. So thank you for all you do with the Global Math Department.
Oh, well, no problem. I'm glad that we had the opportunity to share all this work with teachers from around the world. And speaking of around the world and how many people we reach, we actually have over 13,000 members actually in our list of subscribers. And because of that, I'm having a little bit of difficulty actually emailing the link for next week's presentation, because we can only send out 10,000 emails in a given day. So I have to figure out how to work around that problem. But I'm going to post the link to next week's presentation in the chat. So if you actually clicked on that link, you could actually go and sign up for that presentation. Next week's presentation is titled Math Workshop in Synchronous Online Classes, and the recommended grade level is 3 to 8, and that is being presented by Teresa Wills. Teresa Wills is actually an online math teacher, and she shared some ideas probably about a month and a half ago, maybe a month ago. And her presentation then was awesome. So I'm pretty sure the ideas that she'll be sharing next week will be exciting as well. And then just so you know, our final presentation of the school year will be on June 23rd. That presentation had been scheduled for last week, but was moved to this week. So if you already signed up for that presentation that was scheduled for last week, you do not need to sign up for the one on the 23rd. You'll already have the link to that. So thank you very much for being here tonight. And thank you very much again, David.
All right, thank you. And like I said, I'll stick around a little bit if you have specific questions, but very, very, very excited to share anything I might have with you. And Ashwin, I see you're raising your hand. Feel free to type any question you have. Oh, it looks like it's about about next week, perhaps.
Yep. Okay. Yep. If you're registered for next week, that's great. Again, the link is here, and we'll be tweeting that out as well. So thanks to everyone for being here tonight, and the recording will be posted approximately 12 hours from now, so you can share that with others. Have a wonderful evening, everyone.
Yeah, and thanks. Honored that you joined me tonight. We all have different things or better things we could be doing, so really, really happy that so many of you were able to join us tonight. Have a good night or good morning or good day, wherever you are in the world, and thank you very much.